So this is a solution to question 6 of the homework. So we're using the substitution x equals 1 over t squared minus 1 to show that the integral of 1 over root xx plus 1 is 2 log root x plus 1 plus c. And we're given this result here to use without proof in red. And by the way, hopefully you know, the way to prove this result in red is partial fractions. If you write 1 over t squared minus a as something over t minus a plus something over t plus a, then you could prove this result in red. So let's just start by differentiating. So my solution, let's start by differentiating our substitution. So let's work out dx by dt. The way we're going to do that is the quotient rule. The top is 1, so the derivative of the top is 0, and the derivative of the bottom is 2t. So we get a minus 2t times 1 over t squared minus 1 squared. And then let's write x plus 1 in terms of t, because eventually we want to write the whole integrand in terms of t, but let's just start by working out this. So this is 1 over t squared minus 1 times 1 over t squared minus 1 plus 1. And if we write everything over t squared minus 1 squared, we're going to get a 1, and then a t squared minus 1. So that just gives us t squared over t squared minus 1 squared. So therefore, the root of x plus 1 is t over t squared minus 1, because t is greater than 1, so it is going to be the positive root, and this implies that 1 over root x plus 1 is t squared minus 1 over t. So therefore, the integral of 1 over root x plus 1 is simply, well, dx, we know from this that dx is minus 2t over t squared minus 1 squared dt. And then we've shown that 1 over root x plus 1 is t squared minus 1 over t. And then a few things cancel, the t's here cancel, and the t squared minus 1 cancels, so we just end up with minus 2 integral of 1 over t squared minus 1 dt. And then we can apply the result we were given in red with a equals 1. So we have minus 2, and then a is equal to 1, so we've got 1 over 2 times the natural log of t minus 1 over t plus 1 plus c. And now we just need to do quite a lot of manipulation to show this is equal to 2 natural log root x plus 1. So this is minus log t minus 1 over t plus 1 plus c, which is the same as log of t plus 1 over t minus 1 plus c. And then let's replace t with, well, we need to work out what t is in terms of x. So let's do that next. So we'll just do that at the side. So we've got x is 1 over t squared minus 1. So t squared minus 1 is 1 over x. So t squared is 1 plus 1 over x. So t squared is x plus 1 over x. So t is root x plus 1 over x. Okay, so we're going to get natural log of, oh, and by the way, because t is greater than 1, we can drop the modulus signs now. We can just use brackets. So we've got log of root x plus 1 over x plus 1 over root x plus 1 over x minus 1 plus c. And this, now if we multiply top and bottom of the fraction by root x, we obtain this. And now if we rationalize the denominator, we're going to get So we would multiply top and bottom by root x plus 1 plus root x, which would give us just 1 in the new denominator. So we're going to get root x plus 1 plus root x squared. And then the 2 we can bring outside the log. And this was precisely what we were asked to show, so we're done. And then there was a second part to the question. The second part, let me just find it. So the second part is the section of the curve y equals 1 over root x minus 1 over root x plus 1 between x equals 1/8 and x equals 9/16 is rotated 360 degrees about the x-axis. Show that the volume enclosed is 2 pi natural log of 5 over 4. Okay, so we're just going to apply the formula for the volume of revolution. When something's rotated about the x-axis, it's pi integral of y squared dx, where x for us is between 1/8 and 9/16. And then, well, what is y squared? So y squared is 1 over x plus 1 over x plus 1 minus 2 over root x plus 1. That's just squaring the expression we've got for y. And then we know integral of 1 over x is natural log of x. And we don't need to bother about modulus here because we know x is positive. And then for this last integral, we're going to use what we've just done. So by what we just did, this is minus 4 natural log of root x plus 1 plus root x. And again, that's between 1/8 and 9/16. And then we'll substitute everything in. So we've got pi times log of 9/16 plus log of 25/16 minus 4 log 2, and then minus log of 1/8 minus log of 9/8 plus 4 log of, let's see, root 9/8 plus root 1/8. I think that's, so that's just 4 over root 8, isn't it, which is root 2. So this is 4 log root 2. So maybe we'll just get rid of this. So now this is equal to pi, and then let's combine the first two terms together. So this is log of, well, okay, so maybe these two terms are log of 3/4 squared plus log of 5 over 4 squared. So this is 2 log of 3/4 times 5/4. So this term is 2 log of 15/16. And then the next, and then let's look at the 1/8 and 9/8. Similarly, if I combine those together, I'm going to get minus 2 log of 3/8, I believe, because log 1/8 plus log 9/8 is log 9 over 64, which is 2 log 3/8, because 9 over 64 is 3/8 squared. And then I've got 4, the other stuff is 4 log root 2 over 2, which of course is, well, yeah, so there are some things we can do with that. So we'll look at that in a second. So then, if I combine together these two terms, I've got 2 log, and then we're going to divide 15/16 divided by 3/8. So that's the same as multiplying by 8/3. So that's 15 over 6, but then it's just 5 over 2, isn't it? And then this is 2 log, and then if we square root 2 over 2, we get a half. So this is 2 log a half. And now if I combine together, we've got 2 pi log 5 over 4 as required. Done. So that's the solution.